Hello, calculus students. Mr. Klein here to teach you a little bit about the extreme value theorem. You'll notice that I'm wearing a hat. That's fun. You'll also, if you listen carefully, you might be able to hear there's all sorts of banging upstairs. I think that my daughter is in gym class right now. So what does it mean for something to be extreme? It means that it has a very large value, or it means that it has a very small value. And while we've talked about a type of extreme called a relative extrema before, today we're going to be also talking about something called an absolute or a global extreme. So let's review what it means for something to be a relative extreme. It means that it has the biggest value in a neighborhood. And a neighborhood is also known as an open interval of points. So for example, if you looked at the first graph right here, we would have a relative extreme at B because it has the largest value in that neighborhood. Now you would be tempted to say that we also have a relative extreme at C, but that is not true. And the reason is because C does not have a set of points around it. There's only points on one side. So this open interval can't be an endpoint. I would like you to tell me, where are all of the relative extremes on these graphs? So hopefully you said that they are at B, at E, and at G, and that is it. So there are relative extremes. Now, what do all of those points have in common? Boom, boom, boom. They are critical points. What does it mean to be a critical point? It means that the function is continuous and the derivative at that point is 0 or it is undefined, right? Undefined at the cusp, 0 at this maximum and this minimum. Now, are all critical points going to give you a relative extreme? No, because you can see you get values like J right here, which has a slope of 0, but it is not a relative extreme. So that's review. Here's the new stuff for today. Absolute extrema. An absolute extreme is any value on a function that has a value greater than everything else on its domain, so on the entire graph. So to give you a quick example, for the first function here, not only is B a local extreme, it is also a global extreme. I will mark them in red because B has a value greater than everything else on the function. C would be a global minimum because its value is less than every other point on the function. Okay. I would like you to identify the rest of the global extremes. Okay. So hopefully you identified that E has the maximum value here. G has the absolute minimum. Hopefully you identified that here, I has the absolute minimum and that there is no absolute max. Because we have an open point here. Okay. Finally, because of the asymptote, there are no global extremes on this last graph. There is no maximum value. There is no minimum value. Okay, so now we're looking at these global extremes here, 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 and here. And I want you to identify what kind of points they occur at. Well, hopefully you notice that there's only two kinds of points that it can happen at. It can happen at the critical points, like here and here and here, right? Those are critical. Or it can happen at points like this one and this one, which are endpoints. And that right there is the extreme value theorem. The extreme value theorem says this, that the absolute extrema only occur at critical points and end points. They will not happen anywhere else. You have the Mr. Klein guarantee. Okay, let's give these a try. If you take a look at the bottom of the page, we've got some true false questions that are going to see if you understand what's going on with these relative and absolute extrema. Give them a try, and then I'll give you the answers. Let's go through the answers to the true false questions. A says local extremes occur only on the interior of the interval. That is true. We talked about that already. B says every critical point of a function is a relative extreme of the function. That is false. Here's why. Look at this example. This is a critical point. Why is it a critical point? Well, because the derivative at this point would be equal to 0. However, it is not extreme. So a plateau would be an example of a point that makes this statement untrue. If you take a look at C, it says every curve on an interval has a global extreme value. An easy way to see that that's false is to look at one like the last graph where there was an asymptote, right? If you have an asymptote and you have a function going forever in one direction or in both directions, then you're not going to have global extremes. D is true. D says that if a function is always increasing, it has no local extreme values. And the reason that that's true is because if it is monotonically increasing, that means that its minimum, its global minimum, has to occur at the start of the interval, and its global maximum has to occur at the end of the interval. Okay, that brings us to E, the last one, which is that if a function, if x equals c is a local min or a max, then the derivative must be 0. Now, it is most of the time, but it's not always true. And the counterexample is when you have a cusp. At a cusp, the derivative is undefined, but a cusp can be a global min or a global max, a local min or a local max. Okay, looking at example number 1. This is one you should be able to do without a calculator. On this problem, it says, let's suppose that you got this function. It's a cubic function. And let's suppose that we're also given a domain. So we're starting at -2 and we're ending at 3. Those are our endpoints. And what we want to do is we want to identify the global minimum and the global maximum. Each one of these is a two-step problem. I'm actually going to begin by talking about step 2, because I think that it will make step 1 make sense. Step 2 is to test the candidates. Sort of like an election. And in this election, you want to figure out who's the best, who's the maximum, and who's the worst, who's the minimum. But keep in mind that between -2 and 3, there are infinitely many x values, and we can't test all of them. So the only candidates we're going to look at are the ones where the maxes and mins can actually happen, which again are at the critical points and at the endpoints. What are our endpoints? They are -2 and 3. The extrema could happen there. What are our critical points? Well, I don't know. That's where step 1 comes in. Step 1 is going to be to find your critical points. And so we would do that this way. We would start by taking the derivative of our equation. which would be 6x squared minus 6x minus 12. And then we're going to set that equal to 0. I'm going to factor the 6 out. If we factor the 6 out, we get x squared minus x minus 2. And let's factor that trinomial into x plus 1 and x minus 2. Does that look good? Yeah. Okay, so what does that tell us? That tells us that we are going to have a critical point at 1, and we're going to have a critical point at 2. And then you just check and make sure that these are in the interval. They are. Both of these numbers are between these two numbers. So I'm going to add -1 and 2 to my list of candidates. You'll notice that I put them in order from the least value up to the greatest value. That's a good way to do these things. It keeps you organized. What we're looking for is the largest value of f. So we're now going to test these values by plugging each one of them into this function. I've done this already. When I plugged -2 in, I got 0. When I plugged -1 in, I got 11. When I plugged 2 in, I got -16. And when I plugged 3 in, I got 5. So you just look at these values, whichever one is largest, that's your global maximum. So the global maximum is going to occur at -1, and the maximum value is 11. That's how you would answer this question right here. If it doesn't say anything about the x value, give the y value. This is the actual maximum. The global minimum would occur at 2, and it has a value of -16. So there's the answers to the question. Now, I'd like to go just a little bit further with example number 1 and say, let's suppose that all we wanted was this one right here, just the global max. It turns out that we can simplify matters for ourselves a little bit. And the way that we're going to simplify is we're not going to have to plug all of these numbers in because they can't all be the max. Here's what I mean by that. Imagine back in step 1, we had made a sign chart. By the way, for this kind of description of just finding the max, I'm going to do everything in red so you can see the difference between the original problem and the modification I'm making. So -1 and 2 both give us a 0. And if we make a sign chart, we're going to find that it is positive here between 2 and 3. 3 is our endpoint. Negative on this interval. And then positive on this interval between -2 and 1. Okay, so you know how to make a sign chart. Well, what good does that do for us? It tells us a little bit about what the graph of f looks like. Specifically, it tells us that the graph of f must be increasing and then decreasing and then increasing. It doesn't tell us how much it's going to increase or how much it's going to decrease, but it tells us what direction we're moving in. Well, look here. If you know that this is going up and then down and then up, suddenly rather than having 1, 2, 3, 4 candidates for your global maximum, you only have 2. You've got this relative peak right here and this end point right here. The moral of the story being, if you draw the sign chart first, you can come over here and you can now reduce by saying, I don't have to test this value and I don't have to test this value because I know that they're going to give us minimums. I'm only looking for maxes. Okay, let's keep that in mind as we go to the next example. Let me pause the video for a second and read over example number 2. Coffee is good. All right, what we got going on here? An integral function. We know that as soon as we see an integral function, the first thing that we are to write down is that the rate of change of the function is the integrand. So g prime of x is f of x. And this is f over here. Which means this is a different kind of problem because unlike the last one where we had to cook up the derivative and then draw a sign chart, here we basically already have a sign chart, don't we? This is the derivative. So what we should note is that the derivative has zeros here, 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 and here. And let's just separate this so that we can see our signs. Our sign chart kind of goes like this. Negative, positive, positive, negative, negative. Which means that while we don't know exactly what G is going to look like at the moment, we do know this. We know that it is going to, let me make these a little bit longer. We know that because of the negative value on its rate, it's going to decrease, and then it's going to increase. It's going to level off, then it's going to increase some more. Then it's going to decrease. Then it's going to decrease some more. All right, so now that we know that, what are our x values that are candidates for the global max? I see two of them. I see right here at the beginning, and I see right here at 6. Now keep in mind that even though I drew it so that this one looks like it's bigger than this one, that's not necessarily the case because I didn't know how much this was going to increase by. I was just drawing down, up, down. Okay, so our candidates for the global max will be at -4 and at 6. And our candidates for the global min would be here at this low point, and then here at this low point, at -2 and at 12. Note that some of the zeros, the 2 and the 10, the places where the rate graph bounces off of the x-axis, even though they're critical points, there's no way that either this one or this one is going to give us an extreme value. Okay, so next step, it is time to test the candidates. So you can think of what we did right here and right here as step 1. Now we're moving to step 2. So our x values that we're interested in to find the global min and the global max are going to be at -4, -2, 6, and 12. We're going to be plugging those in to this function. Okay. I'll plug the first one in with you. If we plug a 4 in, that would give us the integral from 2 to -4. I meant -4, not 4. Of the function. And you want to notice here that our endpoints are backwards, right? -4 is smaller than 2. So you want to flip those around. When you do that, it's going to change the sign. Now we come over here, integral from -4 to 2. Here's -4. Here's 2. I see that we've got this region, which is negative, and it has an area of 2 multiplied by 4 divided by 2. So that would give us -4. And then these are both the same area, aren't they? The triangles are the same shape. So this will be a +4 and a +4 because they're above the x-axis. So that means that this would be equal to -4 plus 4 plus 4. which is going to give us overall a -4. All right, let's pause the video for a moment, and I would like you to go and find the other three values here. All right, let's check our work. This is what your work should look like. The problem asks us for the global minimum. Now, as I'm looking here, the global minimum is occurring at -2, and it has a value of -8 because that's the least that we got. And then the global maximum would be 8.